Okay, let's get started in section 6.3. We're talking about the multiplication and division of rational numbers. Okay, so I want to start off by reminding you that the motivation for multiplication is repeated addition. So we have a set model here, and let's start off by just coloring in. We have 3 models, and we're going to model 3/4. So let's just color in 3/4 of each of these. And you don't have to color them the exact same way. In fact, your students often won't. So I'll mix it up here a little bit. And then to finish this problem here, what we do is we color the total number of fourths that are colored. So we have 3, 6, 9, a total of 9 colored sections of fourths. Okay, now another way to look at it is, let's go ahead and color in our 3/4 real quick. Sometimes I like to mix up my coloring. All right. Okay, so we have 3/4, and one thing that you can get your students to do is to take the separate ones and then color in a full set. So let's take a look at how this goes. So I'm going to color in this first 3 here. And then we're going to fill in the next set of 3 here. And finally, that last set of 3. Now this is a cool way to do this, because this not only shows us that we have 9/4, but it also shows us that we have 2 full and 1/4 left over. This is a mixed number, and we'll talk about this later, but this is a good way to make the connection with mixed numbers. Okay, another method is the bar graph model. Okay, the bar graph model is pretty cool. I really like it, and I'm going to motivate this example with a word problem. You'll be doing that a lot in your classes, motivating examples with word problems. Students are going to have word problem driven worksheets, problem solving, and then they'll do drills to build their skills. Okay, so let's take a look at this bar graph model. So the idea is first to model the first graph, or the first fraction, I'm sorry. Let's model the first fraction of 3/5. And you want to do that using vertical bars. Doesn't mean that you got to color it in vertically, but it means that you want to have vertical bars to represent those strips. Okay, and I'm not sure why I drew 2. I'm not even going to worry about it. I'm just going to mark this one out, and we're just going to do this one example, so I'm not coloring everything twice. Okay, so the first thing is to model the first fraction with vertical bars to separate the units. And then the next stop, oh wait, but let me point out the fact that this represents 3 out of 5, right? That's the 3/5. Okay, now next what we do is we look horizontally and we model that fraction in the horizontal way. So I'm going to split that guy in half, and notice that this is, and if we color here, this is 1/2. So when we multiply those two together, the way we put that number together is the intersecting units become the numerator, And the total number of units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, becomes the denominator. Okay, so let's look at a couple more of those. Let me change over to a highlighter since these are already drawn. So the first thing we're going to model is 4 out of 7. So we're going to do these 4 rows. Out of the 7 rows, let me show you that that is 4 out of 7. And then let's go the other direction and do 2/3, and it doesn't matter which 2/3 that we choose, to be quite honest, and you're going to have kids that are going to want to do, you know, one side. Oh, I should have gone with the thicker. One side and maybe the other side instead of the 2 that are next to each other. Okay. Now what that represented right there, as we see, is 2/3. And so just like the last example, what we do is we count where they intersect. So 1, 2, 3, 4, 5, 6, 7, 8. So our numerator is going to be 8 over the total number of squares, and the total number of squares is actually 3 rows times 7. 3 times 7 is 21. Okay, now I want to remind you that when you see the word of, and this is a big confusion for a lot of students, that does mean the same thing as 2/5 divided by 1/4. Also, just as a note, it also means 2/5 divided by 1/4, which is considered a complex fraction when you write it like that. Anyway, side note over. All right, I don't really like how my thing turned out with the highlighter over there, so I'm just going to stick with the colorings. Here we're looking for 2/5, so let's first 1, 2, 3, 4, 5. This is where we're going to go, and I'm going to go these 2 rows. Okay, and that represents 2/5. And now we're going to do 1/4. So 2/5 times 1/4 is equal to 2 over, and let's see, 4 times 5 is 20, and then we can simplify that to 1/10. Okay, awesome. All right, let's get to the next one. So that brings us to the definition of the multiplication of rational numbers. It says if A over B and C over D are elements of the rational numbers, then A over B times C over D is equal to A times C over B times D. What I tell my students, okay, so you notice you get to multiply straight across. What I say to my students, even now in my college classes, is shirts times shirts over pants times pants. Meaning you multiply across the top and you multiply across the bottom. And for some reason, the ridiculousness of shirts times shirts over pants times pants sticks. Anyway, just a little side note. Okay, multiply multiplicative identity. The multiplicative identity is still 1, just like it was for whole numbers, just like it was for natural numbers, just like it was for integers. The multiplicative identity is 1. We do employ the multiplicative inverse here, which is something that's a little bit new. The multiplicative inverse for a rational number is that fraction flipped over. So we know that two fractions are multiplicative inverses of each other when you multiply them together and they cancel out to equal 1. Okay? So B over A is the multiplicative inverse of A over B. So if we had 5/3, the multiplicative inverse would be 3/5. If we had negative 2 over 1, the multiplicative inverse is going to be negative 1 over 2. Okay, sign doesn't change to be a multiplicative inverse. Properties of rational numbers, the general properties, the commutative property, the associative property, those kinds of properties are still exactly the same. Same with the distributive property. I put a couple here for us to make note of. The multiplicative property of equality, when you know that two rational numbers are equal to each other, then if we multiply the same number on both sides, it's still going to be equal. We'll use this guy in conjunction. We'll use this with multiplicative inverses. To solve problems. Okay. Also, I took the time to remind us of the multiplic. Let me take a drink. Obviously, the tongue is not operating. Multiplicative property of the inequality. Remember, the thing that you have to remember here is when you multiply by a negative number, it flips the inequality. Okay, so multiply or divide, by the way, or divide by a negative number, then flip the inequality sign. And we talked about all that before. So basically what I talked about before about inequalities translates here. And then of course the multiplicative property of 0, anything times 0 is 0. And we know that, but it is to be pointed out. Okay, let's take a look at a couple of applications here and how we could solve these. A bike's on sale for 3/4 the original price. If the sale price is $330, what is the original price? So I have two different ways to do this. Here on the left-hand side, we're setting it up as a multiplication problem. We know that 3/4 of the unknown price is equal to this $330. And so we kind of set that up. And then we use that multiplicative inverse and the fact that if two things are set equal to each other, we can multiply by the same value on both sides without changing the problem. Then that's what we did here. And so we used the multiplicative inverse of 3/4 and multiplied both sides by 4/3 and got the answer of $440 was the original price. Now that's a very algebraic way of thinking about it, and depending on what level classes you're teaching and depending on the level of comprehension from your students, you might need to have an alternative way of solving the problem, or your students might just see this alternative way. So visually, you know, 3/4 means 3 of the 4 bars represent $330. So I'm just going to cover this up like this. And all of this is equal to $330. So $330 divided by 3 means they're each worth $110. So we can surmise that this guy's worth 110, and this guy's worth 110, and this guy's worth 110. So if those 3 pieces are worth 110, then we know without a doubt that this guy is worth 110. So you can take from there 2 ways. You could add all these up to equal 440, or you could have said 330 plus that additional 110 made 440. Couple of different ways to do that. Let's look at the multiplication with mixed numbers. I felt like it would be neater if I didn't write this, because I know that even though my writing on the units that I use at the college, the Wacom tablets are super smooth. What I wind up using here is not quite the same quality, and so it's not quite as smooth. I'm going to look to getting an updated one, but anyhow, so I decided I would type this up, so let's talk through it. So we're going to start here with our 2.5 times 3 1/4, okay? And the definition of a mixed number is 2 plus 1/2. And so we're going to rewrite this. So say we have A over BC, and maybe my PowerPoint is off, or maybe I missed some of my notes, but I swear I'm going to talk to you about this. But let me make this point. Maybe things got out of order. Apologies. So I'm going to rewrite both of these guys, the first one being our 2 1/2, second one being our 3 1/4, and then we're going to use that distribution property where we take each thing in the first parenthesis and multiply it to the second parenthesis. So here's the 2 multiplying by the 3 plus 1/4. And then here's the 1/2 multiplying by the 3 and the 1/4. And then we use that again. And now here's our 2 times our 3, our 2 times our 1/4, plus our 1/2 times our 3, and our 1/2 times 1/4. Then we just start kind of doing the math here. We put these 2 together equals 6. 2 times 1/4 is equal to 1/2. 1/2 times 3 is equal to 3/2, and 1/2 times 1/4 was equal to 1/8. And then I just looked to see where I could put things together easily here, and 1/2 plus 3/2 is 4/2, which is 2. So then I have our 6 plus 2 plus 1/8, which saved me from doing a whole lot of awful fractions. We wound up with 8 1/8. Another way to do this is to convert our mixed number to an improper fraction. And to do that in practice, and I think I write this all formally somewhere, we go A times C plus B all over C. So this would be A times the C plus B all over C. Anyway, so here's how we do it. 2 times 2 plus 1 equals 5. over the 2. And here we say 4 times 3 plus 1 equals 13 over the 4. Now we get to shirts times shirts, pants times pantsit. 5 times 13, 65. 2 times 4 is 8. And then I found the mixed number back, and here to do that we need to do the division, and I know you know how to do this from your life, and I really hope I have this, I did not miss this in the notes, but anyhow, 8 goes into 65. 8 times 8 is 64. Make that subtraction with 1 left over. So this is the whole number, the whole part, and then we have our remainder over our divisor is the fraction piece. Okay, so let's recall that, and here's another typo. My goodness, I am too far in now. We're talking about division. I wrote subtraction in here twice, so let me make this correction. And note that I'm not going to record two things basically back to back in a small window anymore. Anyway, recall that division is modeled as repeated subtraction. So 6 divided by 3 means how many groups of 3's are there in the number 6? So we do know that 6 divided by 3 is equal to 2 because 3 times 2 is equal to 6. Okay, so we know that. So when we're saying 3 divided by 1/2, that means how many groups of 1/2 are there in 3? So first, let's model the dividend. Okay, and the dividend is 3. Remember that the dividend is the number you're dividing into. The dividend is the number you're dividing into, and the divisor is the number that you're using to divide in. Okay, so first we model the dividend. That is 3. I've got it. Here's 1, 2, and 3. And then we want to know how many divisors will fit. So the idea is how many halves can we get in here? Well, this is a half, and this is a half. This is a half-ish. This is a half. And again, a half and a half. So we have a total of 6 1/2s here. So 3 divided by 1/2 is equal to 6. Okay, so this can also be modeled with the measurement model. So we start off with our 3. So here's my 0, and here's 1, and 2, and 3. And we want to see how many halves can we get in here. So here's 1/2. 2 halves. 3 halves. 4 halves. 5 halves. 6 halves. Yay. And then finally, another way to do it that really punches in the repeated subtraction idea is take your dividend and write it in terms. So change it over. 3 is equal to 6 over 2 halves, and you start off with that. So whatever your denominator is and your divisor is how many what you need to convert it to. And then we just start subtracting halves. There's the first one. There's the second one. There's the third one. There's the fourth, the fifth. And you do this until you get down to 0. And so, sorry, I clearly forgot about my little circle there. So it equals 6. Okay, let's move on. So what if it's not a whole number? What if it's two fractions? That changes things a little bit, but not a whole lot. We use a lot of fraction circles when we're first introducing and modeling the idea of fractions. Now, I know you know how to do the algorithm. You're the teacher. You know how to do the algorithm. But it is very important that students understand what is actually happening behind an algorithm. Okay, so it's really important that you do these hands-on different kinds of models so they can really like understand the action, and the division sign is not just some magical thing. Okay, all right, so first things first, where we have 3/4 divided by 1/8. And if you have trouble with this, and when you're in the classroom for sure, you want to write down. You want to write down, what does this actually say? And it says, how many 1/8 are there in 3/4? So to do that, first we need to model 3/4. So first we're going to model the dividend here. Let me model it here. So let's color in 3/4. And now from this model, we need to know how many eighths there are. So we've got to now break the circle into the divisors, denominators, pieces, okay? Or maybe the least common denominator. We'll see, okay? So here, I can break these guys into eighths by splitting each one of my pi wedges, each one of my quarters, in half to make eighths. Okay, and now that I have eighths, then we need to see how many 3/4 are in there. Okay, so how many eighths are in those 3/4? And here is 1/8, here is 2/8, 3/8, 4/8, 5/8, and 6/8. So 3/4 divided by 1/8 is equal to 6, because there are 6/8. Okay. All right. So let's look at how to do this with the measurement model. Okay, because measurement models are pretty portable in the sense that it's really nice to use those fraction circles to visualize, but it can get really hairy if you have to break a circle into 24 slices. Trust me, I broke one into 12 and it was hard. So you don't want to be pinning yourself into that. So once you can, you want to move to some of these measurement models, because you can easily draw them. The students can easily draw them without frustrations and stuff like that. So let's take a look at this guy. Now, the first thing you should do with the measurement model is determine the LCD and convert both of your fractions. Okay, and I went over LCD in the last video. I will remind you again how to find the LCD. We're finding the LCD of 8 and 4. You got to find the prime factorization of each of those. The prime factorization of 8 is 2 cubed, and the prime factorization of 4 is 2 squared. And the LCD is represented by the highest power of all the prime numbers that make up the numbers that you're comparing. So the LCD here is 2 cubed, which is equal to 8. Okay, so I need to rewrite my numbers. 7/8 is going to stay 7/8, but I have 3/4 that I need to convert into eighths. So that means that is 2 times 3. So I have 6/8. That is what 3/4 is. So now I'm dealing with 7/8 divided into 3/4. Okay. Now it says to mark your model in the LCD units. Okay, so I'm going to start here with 0, and my LCD units are 8. So I'm going to go 8. So 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. Notice making that line a little bit longer so that whole unit stands out. I'm going to do this a second time. So that's 8/8, 9/8, 10/8, 11/8, 12/8, 13, 14, 15, and 16/8 makes 2. And again, you want to reinforce to your students that 1 is equal to, in this case, 8/8. Okay. Now, the next thing you want to do is indicate the location of your dividend. And so our dividend here is 7/8. So here is 7/8, and I'm just going to locate it. I'm going to use a little dotted line. And the next thing we're going to do is group out the divisor until the entire dividend has been encompassed in a group. So we're going to be pulling out groups of 3/4, but remember 3/4 is 6/8. So I'm going to count out 6. So 1, 2, 3, 4, 5, 6. So there is one group of 6/8. Okay, which is the same thing as 3/4. Now, notice that the whole bunch of 7/8 hasn't been used yet. We've got stuff left, so we're going to have to count out another 6/8. Okay, so we got to go another 6/8. So that's 1/8, 2/8, 3/8, 4/8, 5/8, 6/8. Now, we have encompassed the entire group. This one group of 6/8 didn't do it. It took 2 groups of 6/8 to cover the entire 7/8. So that's our entire 7/8. Okay? Now, when we write the answer is the whole number part of our mixed answer is the total number of groups, and the fraction part of our answer is this ratio right here. There is 1 out of 1, 2, 3, 4, 5, 6. So this is 1/6. I know that's crazy, so I've got 2 more examples for you. To be quite honest with you, I had to sit down and work through a few examples so I knew how to put this, how to articulate it. I saw what they did, but I couldn't understand how to tell you in words. That's a great skill to do. If you're working on something and you're not quite sure, you need to write it down and try to rewrite it in words that you could explain it to someone else instead of showing someone else. It's a great skill to be able to explain how something works. So let's take a look here. Okay, so let's look at our 3/4 divided by 3/8. So the first thing we want to do is we want to consider what our LCD is, and our LCD between 4 and 8, as we just saw a moment ago, is actually 8. And the other thing we need to do is we need to rewrite our 3/4 as an eighth, and we just saw that on the last example that it is 6/8. Okay, so we need to set up our line here, and we need to start off with our 0, and we're doing eighths again. So 1, 2, 3, 4, 5, 6, 7, 8/8. 1, 2, 3, 4, 5, 6, 7, another 8/8. So there's 2. Okay. Now we're going to model our 3/4, okay, which is 6/8. So we're going to model our 3/4. And then it asks us to pull out groups of 3/8. So 1, 2, 3. There's one group of 3/8. And 1, 2, 3. There's two groups of 3/8. Now we encompass the whole thing. So 3/4 divided by 3/8 is equal to 2, because there are two groups. One group, two groups. This is two groups, two full groups of 3/8. All right, so let's take a look at this guy. This guy's 5/3 and 1/2. So the first thing, hopefully, gets noticed is that 5/3 is bigger than 1, right? So we're going to have to at least model 2 of whatever units that we wind up with. So let's find our LCD. Here, our LCD is the LCD between 3 and 2. Both of those are prime numbers, so the LCD must be 6. Okay, we learned that last time. So let's put in our 6. So 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. I don't know why I drew more. Anyway, I did. Okay, good enough. All right. So we also need to convert our numbers over, so because neither one of them are in the units that we have to talk about, not in the same units. We've got to convert both of them over to sixths. Okay, so 3 times 2 is equal to 6, so we'll have 2 times 5, which is 10/6. Which we knew was more than 1. And then 2 times 3 equals 6, so 1 times 3 will give us 3/6. Okay, so let's model out our 10/6. So that's 6, 7, 8, 9, 10. Here we are at 10/6. Okay, and we're modeling out 3/6. So 1, 2, 3. There's one group. 1, 2, 3. There's another group. 1, 2, 3. There's another group. 1, 2, 3. Finally, that last group. Notice again, we have to keep on going to cover all the way through. Okay, got to cover all the way through that 10/6. Now, We indicate how many groups came out evenly, completely with nothing left over. That's 3. And then what do we have left over here? Well, we have 1 of 1, 2, 3. So 3 and 1/3. All right. Perfect. Let's see what else we got ahead. The division of rational numbers. All right, so here's the official definition. A over B, C over D, E over F are all rational numbers such that C over D is not equal to 0. And of course, B, D, and F are also not equal to 0, or they would not be rational numbers, right? Can't divide by 0. So A divided by B, A over B divided by C over D is equal to E over F if and only if E over F is the unique number, the multiplicative inverse of C over D, kind of. I shouldn't have said multiplicative inverse, but I'm going to have to take it back. But I'm too far in to not fix it, okay? Let me get my stuff together and take another drink of my soda real quick. Okay, so in practice, this definition is the stay, change, flip. And I don't know if you know this, but stay, change, flip is the best. And this is how it is. So for this particular problem here, our 7/8 divided by 3/4. The stay part means that you write down the first fraction, not changing it at all. It stays as it stands. The change stands for change the division to multiplication. And the flip is flip the divisor over and perform the multiplication. And 3/4, the multiplicative inverse is 4/3. So we flip it over and there it goes. And then we go straight across. However you want to do it. We get 7/6. And I simplified it to the mixed number 1/6. There's an algorithm of the division of fractions, A over B, C over D. These are rational numbers such that C over D is not equal to 0. Also, B and D are not equal to 0. Then this is true. A over B divided by C over D is equal to A over B times D over C. Okay, so let's take a look at this example. A bookstore has a 37.5-inch shelf. How many 1 1/4-inch books fit in? So what we have here is 37.5 divided by 1 1/4. In other words, we want to know how many 1 1/4s are in 37.5. That's what we want to know. Okay, now we're not going to draw a picture of this, but what we are going to have to do first and foremost is convert to an improper fraction. So 3 times 2, 37 times 2 is 74, plus 1 is 75 halves, divided by 4 times 1 is 4, plus 1 is 5/4. Now we can do our stay, change, flip. So we have 75 over 2 times 4 over 5. 75 times 4, 20, 300. Over 2 times 5 is 10. So our answer is 30. Did I mess that up? I didn't work it out. I don't think. I didn't look. Let me look real quick because my brain is absolute mush at this point. No, it's good. Yay. Whew. My brain is mush. Okay, we're almost there. 2 more slides. We've got this. Okay, the next slide is just to remind you of all those properties of exponents. I want to point out to you that all of the check marks, the bases are the same. Okay, so that would be the exact same number. These others here are dealing with different bases. Point that technicality out to you. Okay, and then let's wrap it up here with some examples. Here, let's apply some of these rules. The one rule, and I just passed by it and I should have stopped and talked about it, but let me over here on the side talk in grand detail, or at least in pretty good detail, about the negative exponent. When you have a negative exponent, that means that you want to flip it over in a sense. So a to the negative n is 1 over a to the n. All right, so the idea is that the negative causes the base to change position in the fraction. Remember, any whole number is also a fraction, so it kind of changes position. Let me show you a couple of other like situations here. So if I had a over b to the negative 2, that would become b over a to the second. So basically that negative just flips whatever fraction you have over, and if you're not dealing with a fraction, then it makes it a fraction because we always have a 1 underneath. All right, so let's get over here to this first example. Here we have 16 squared times 8 to the negative 3. So this is 16 squared times 1 over 8. Notice the negative goes away. It becomes positive 8 to the third. So this is the same thing as 16 squared over 8 cubed. I'm going to do this using prime factors here, and I'm going to kind of make it as easy as possible. Maybe I don't prime factor it all the way out, but 16 is 8 times 2 squared over 8 cubed here. So let's see what that gives us. That gives us, by the rules of exponents, we have this. And then I have 2 of these on top and 3 of these on the bottom. So this gives me 2 squared over 8. And then, oh, this one's never going to stop because 2 squared is 4 over 8. And we know that is 1/2. Sorry, that all ran together there. I'm just trying to get this done. Here we go. We've got 20 squared over 2 to the 4th power. So 20 can be rewritten as 2 times 10 squared, 2 to the 4th power. But no, 10's got 2's in it too. So this is going to be 2 times 2 times 10. I mean, not 10, sorry, 5. All that quantity is still squared over 2 to the 4th. So this is 2 squared times 5, quantity squared over 2 to the 4th. This is 2 to the 4th times 5 over 2 to the 4th, which equals 5. Let's do this one. So here we're multiplying, we're distributing. This number is multiplying to all of these things here. So we have 10 to the negative 1 times 10 cubed plus 5 times 10 to the negative 2 times 10 cubed plus 3 times 10 to the negative 3 times 10 cubed. Now we're going to use the rules of exponents here and deal with these tens here, right? And so if we have the same thing, so this rule is a to the n times a to the m. This means the bases are the same, equals a to the m plus n, so we get to add them. So 10 to the negative 1 times 10 to the third power is 10 to the negative 1 plus 3 power plus 5 times, we're going to do the same thing here, 10 to the negative 2 times 10 to the 3 is 10 to the negative 2 plus 3 power plus 3 times 10 to the negative 3 times 10 to the 3 is 10 to the negative 3 plus 3 power. So let's keep on going. 10 to the negative 1 plus 3 is 10 to the negative 2, 10 to the second. 5 times plus 5 times 10, negative 2 plus 3 is 1, plus 3 times 10 to the 0 power. Anything to the 0 power is equal to 1, so this is equal to 100 plus 50 plus 3, which is 153. And then finally, this last guy here, each of these items, hold on a second, let me show you which rule this is. This is that a times b to the n is equal to a to the n, b to the n. Notice these are different bases, not the same base. These guys are different bases, not the same base. So that means that we get to say x cubed to the negative 4 times y to the negative 2 to the negative 4. X cubed to the negative 4, when we take a fraction to a fraction, or we raise a power to a power, sorry, I'm going to just bring this point home here when we have a to the n to the m power, raise a fraction to an exponent to an exponent, we get to multiply the exponents. So this is going to be x to the negative 12, y to the positive 8, and then we always want to write our answers without negative exponents, and to rewrite this x, because it has a negative 12, it's going to go to the bottom and be x to the positive 12 on the bottom and y to the 8th on top. Okay, we made it. I apologize for being so tongue-tied. Absolutely will not, in a course of a couple of hours, record 2 classes. So way too much. All right. Y'all have a good day.